Okay, students, let's get going. We're going to do a lot of sketching today on the document cam. And I hope that you brought some graph paper. If you didn't, you're going to want to have some graph paper. Here's what I have, and it's just cheap graph paper. You don't, for this kind of stuff that we're doing, you don't need fancy engineering paper, but we're going to be using that in a few minutes and doing several sketches. Well, let's just have the chit chat club for the next 2 hours. How about that? You guys are tuning me out. That is a bad thing. Because on the exam, you're going to feel tuned out because you don't catch what I'm teaching. Try to stay with me. Just follow and keep up. Now we're going to talk about something called ray optics today. And well, I don't see hardly anybody looking at the screen. Why is that? Because this guy here on the screen, he's got a little problem there. But yeah, we're going to try to get a handle on this situation here for this guy. See if we can heal things up. Chapter 25 is where we are. So we dipped a little bit forward at, I think, chapter 28 or 29 for polarization. Now we're back at 25. Let's get down to it. Okay, we're going to talk about rays and mirrors mostly today. Hopefully we'll get to talk a little bit about refraction of light towards the end of class. One of the things that I want to emphasize too, you have your clicker ready because we have a clicker questions, 2 clicker questions coming up on this diagram. And the concept I want to emphasize to you is something called equal phase. Now we've talked about this. The different parts of a wave can be labeled in terms of the phase angle from 0 to 2 pi. So for instance, if you count, let me get my cursor over here. If you count the very left side here of this diagram where the 2 sine waves connect, the red one for the magnetic field, the blue one for the electric field, if you consider that to be 0, then the top of this bump, the first bump, would be pi over 2. Now there's another part of this wave where you can say that the phase is equal to pi over 2. All right, and that's right down over here. The next bump, the top of the next bump in this wave. All right, and so that's a quarter of the way through the cycle. You've hit the bump. If you consider this to be 0 down here. All right. Now, an alternate is you could call this one here 5 pi over 2. Okay. In other words, 2 pi plus pi over 2. 1 full cycle plus a quarter of the next cycle for 5 pi over 2. But a lot, most of the time you want to think of this as your pi over 2 point. All right. Now, similarly, this one down here, pi, halfway through the cycle. All right. Now, I'm going to ask you a multiple choice question. But before we do, let me pause for questions. Yes.
So a full cycle would be
Yeah. So you're saying right here? Yeah, that would be 2 pi. And it's another 0, or you could call it, that's the next 0. You know, so you call either 2 pi or 4 pi or 88 pi. You know, it depends on where you start counting. That's all. But it's a periodic function. So you're basically, so if you know 0 to 2 pi of the sine and cosine function, you're golden. You know, you just got to. All right, so let's do a multiple choice question, actually 2 of them. And it'll be about that same diagram. Now, here's your question. I want you to think carefully. Multiple choice. Where's the next? Place where phi is equal to pi. Greek letter phi, lowercase phi, is frequently the symbol for the phase. Because it's a PH sound, I guess. Can you make a count, please? Destiny, you forgot to get your pen. You forgot your pen yesterday, last time. Thank you. Thank you. "20 seconds to vote, starting right now. 20 seconds. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh my goodness, we got some splaining to do. All right, now here's what we got. Looks like we got a little bit of B and a little bit of D. Now the correct answer is D, and B, point P2, point P2 is not a phase equal to 0, a phase equal to pi. It's equal to 0. That would be the next. That would be the start of the next cycle. If this over here, the far left, is 0, then this is another one, either 2 pi or 0. No matter how, depending on how you want to do it, right? Now the next one, the next half cycle after that is right here at point P4. So there's your angle. There's your solution. Go ahead and make a note of that in your sketch. And you guys, the reason that we're going to be talking about this phase business is because in ray optics, we think of waves as, we can think of rays, light rays, as being perpendicular to something called a wave front. And a wave front is a zone of equal phase. All right, next question, multiple choice again. What is the phase phi of the E field at point P1? All right. Good, that's what I got here. Actually, I think it should be it should be up to 74 now because one student came in. Kendra, could you do a first aid run for me? Could you do a first aid run to the beverage machine and get me some water? Thanks. 20 seconds starting right now. Ten seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see how you guys are doing on this. Oh ho. Huh. It looks like you guys are getting with the program. 94% of you got this one correct, so that's good. All right. Now, so that's just a little workout. The reason that that you want to think of it as being 3/4 of the way through the cycle, point P2 again is where the cycle, that first cycle finishes. So, all right. So at point P1, you're 3/4 of the way through. All right. Now, thank you. The reason that we want to focus on this is the following. The idea that wave fronts and rays are perpendicular to each other, and a wave front is defined as a surface of equal phase. So everywhere in the wave where you have pi over 2, for instance. Ooh, this is nice. Cold, nice water. Now the image part A is from a spherical light source, and it's putting out spherically curved wavefronts. So, you know, so here's the way that we usually do it. Every part of the wavefront where all the waves have phase pi over 2, for instance. So the distance between these two wavefronts here, that's lambda. All right. So two consecutive wavefronts are separated by a full 2 pi. In other words, spatially, wavelength, one lambda. All right. Now, if you're very, very far away from any shaped source, you'll have plane wave fronts, and that's where they don't have any curvature or not a whole lot of curvature. So we approximate them as plane waves. So and so those two plane waves. So those two plane waves could be the places on that set of rays or on that set of waves where the phase is pi over 2. And then this one's the next one where it's pi over 2. The distance is a lambda, a wavelength between consecutive surfaces of equal phase. All right. Now, every light source, every source of waves, if you're far enough away from it, no matter what shape, the wave fronts are going to be parallel, like, and you can approximate them as plane waves. So that's like saying that if you drop a stone in a pond, if you drop a stone in a puddle, the puddle's not very big, so you'll see the waves going out in the shape of a ring, and then they'll hit the edge of the puddle, and then they'll be absorbed by the ground, right? But if you're in a lake, a still lake, and you drop a pebble on one side of the lake and then go a mile away to the other end, you know, by zip line or something, and watch those waves come in, they're going to come in parallel, like these plane wave fronts, okay? And technically, yes, they are spherical or circular, anyways, for waves in a pond, surface waves, surface of a lake, but they'll be pretty close to and indistinguishable from plane waves. Now, I want to give you kind of a cool website that has a lot of nice simulations about this. Now, unfortunately, it's up at Florida State, and that is a tragedy. So we're going to erase that from existence, and just burn it out of our memories. But do write down this one, and it's about microscopes. So, you know, I'm not big into microscopes. I'm big into telescopes and stuff. But a lot of the stuff is similar. You know, it's quite handy for understanding ray optics and wave optics both. And they have some nice simulations that you can mess around with. Now, let's get down to business. We're going to talk about mirrors first, okay? And mirrors can be flat or they can be curved. But no matter what, if you have a mirror, it's nice and smooth, you know, it's been nicely polished, so it's not too rough, then the law of reflection is fairly simple. The incident ray, the reflected ray, and the normal to the surface, that's that black dashed line in the diagram, they all form a plane. All right, so basically the normal and the incident ray form a plane, and then the reflected ray is going to be in the same plane. Now the angle of incidence equals the angle of reflection. So theta subscript I, that's the angle of incidence. And it's customarily measured from the normal axis, the normal to the surface. And that's because the normal to the surface is what we want. But if we have a curved surface, you know, like a spherical mirror, we can still use this law, even though the surface, if you measured the incident ray, instead of between the ray and the normal, if you went from the ray down to the surface, for a curved surface, where do you go? What do you consider to be the other end of the angle, or the other side of the angle? So, huh? Yeah, right. Except then everything is going to be that's actually a problem and much more difficult. Okay, geometrically, it's much more difficult to work that out. So what we normally do, we customarily say, all right, let's go with the normal, and that's going to be unique no matter what the shape of the surface, flat or curved, and then measure the angles incoming and outgoing. So as I mentioned, everything that we do boils down to this law: flat mirror, spherical, parabolic, hyperbolic. Parabolic is the shape of a mirror that you use if you want a spotlight. All right. So a beam like in a movie theater where they want the light on one person and one person only, you know, for dramatic effect. But for a floodlight, you might want some other kind of surface. So your headlights, I don't know. I'm guessing that headlights are not perfectly parabolic, but they're probably fairly close to that. And we're going to talk about why that is in the next few sketches. Okay, so what we're going to do right now is go to the document cam. And I'm going to continue to record. And we're going to do a flat mirror on the document cam. And can you switch me over to doc cam, please? And okay, here's this. Can you get that up off the floor? We don't want to have any tragic bass fishing accidents or anything like that. All right, now today I'm going to make my sketches on sideways. So here's my graph paper, and this is backed all the way up. I'm going to turn it sideways like this, all right, because I'm going to need an optic axis. All right, so the first thing you want to do is draw through the middle of your paper a vertical line like this to represent a flat mirror. All right. Now we're going to do flat mirrors first, and then we're going to do some convex and concave mirrors. All right, now through the middle of it, can you guys find me a straight edge? We're going to draw an optic axis. Let me see if I can get a straight edge. Is there one over there? Yeah, meter stick's a little bit too big. Anybody got a straight edge? You know, a regular notebook size straight edge? Yeah, this will work. Thanks. Nice. Ooh, quick thinking. All right, so here's my emergency straight edge. All right, I wish this thing could move, but all right, so let me draw. You know, this is burning my chops here, this thing here. Okay, so let me draw. Now, so this is perpendicular to the mirror. All right, so there's my optic axis. And it's pretty important for what we do. Now, what we're going to do is draw a picture of, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to go 10 blocks out to the left, and I'm going to draw a stick figure of a guy that's running. All right. And the top of his head is 2 blocks above the optic axis. Okay. So there's my little stick figure of a guy dashing for the bus or what have you. Okay. Now the top of his coconut is 10 blocks out. So 10 units from the mirror. Now that's an important distance. All right. Now, angle of incidence equals angle of reflection. Let's take a ray of light that, by the way, if you look around the room and you can see anybody's head, the reason that you can see somebody's head is that light is coming from that person's head. It bounces off. It comes from the lights above, bounces off, reflects off, and it's not flat. It's called diffuse reflection, but it goes in all directions, and you can see somebody in this room from all directions, right? And so it reflects into your eye. So let's say that there's a beam of light that goes from the top of his head. I better put on my specs. Man, these things are dirty. Oh my goodness. My x-rays, because I can't use x-ray vision. So I would harm you guys' health. All right, so I'm going to put a dot up here at the top of this coconut. All right. And I'm going to draw a line, a ray, from the top of his coconut, which is 2 units high, to the mirror at a distance 1 unit up, 1 block up, right here from the center. So here's the center and I'll put a letter C here for the center of the mirror. That's actually an important point. So now let me tilt my, all right. So here I go. I'm 10 units out to the left, and I intersect the mirror right here. So here's a light ray So if you're kind of short, or if you're sitting down and you're sitting right here where my pencil is, you'd see the top of that guy's coconut. All right. If you're at the mirror, you'd see, something else. Now, it has, so the angle of incidence is right here, theta. All right. So draw in the normal. Okay, I'm drawing in the normal as a dashed line. All right. Now, the angle of reflection also goes down 1 and over 10. So the angle of reflection, or the outgoing ray, is going to go out at the same tilt angle. So that goes out to the bottom of his foot. All right, so that's one ray. All right, and let's just say that he's on a clear glass surface, and so the ray keeps going off in the same direction. Okay, so those two lines, if you're on graph paper and you have a straight edge, you can draw those lines very accurately. All right, so I'll put an outgoing arrow here. So there's one of the outgoing rays. All right, now that ray is going out here. Now let's draw another one. All right, let's draw another one. Let's see. Let's see now. Let's draw one right down to C. All right, and I'll do this one in red. Okay. So from the top of his cranium down to the center of the mirror. And of course, this one's the easiest of all because it just goes out at the same tilt angle again. All right. So this one's going to go down to and over 10. So that means it's going to go right to here. And so my outgoing ray is like this. Oops. All right, so here's my outgoing ray. All right, now those are two outgoing rays. All right, now I'm going to put a gigantic letter U out here. You are here. If you are here, you see the image, and I'm going to put in parentheses the word in the mirror. It's not really in the mirror, and I'm going to show you why. You see, so this is your big eyeball. This is a little tiny man. This is an Ant-Man. All right. So your eyeballs may be out here somewhere, and you're able to see both of these rays. Now those rays appear to be coming from way back here. All right. So let's draw those rays backwards and see where they end up. See where they intersect. All right. So this one, we know it's going to be 2 blocks, 10 blocks over, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and up to. All right, so it's going to go right through there. Let's see if I can do this without. All right, now draw this as a dotted line. And mine is red dotted line. And just keep working it on out. Okay. You see that ray as coming from somewhere along this line. Now let's do the other one. The first one that I did, this one's in pencil. Okay. And that's this ray here Now it's coming out here to your eye, but it looks like it's coming from way back here. So now this one is 10 units over and 1 block up. So let's go 10 units over, 4, 5, 6, 7, 8, and 1 block up. Okay, so it seems to be coming. No, it's 10 blocks over and 1 block up from here. Oh, it seems to be coming from the same point. Oh my goodness. Look at that. 10 blocks over, 1 block up, dotted line. Perfect intersection right here. And that, my wonderful students, is the location of the coconut of the running man. All right? And he's running towards you, even though in reality he's running towards the mirror. All right? So everything's flip-flopped. All right? Now this is for a flat mirror. And this distance here is 10 blocks, and I'll just put 10 here and out here 10 here, 10 blocks out. And so the moral of the story is the following. The image in a flat mirror, and in parentheses, is as far behind the mirror as the object is in front of the mirror. So that means if you have to, who in here has really weak eyes? They have to have really strong. Did you ever notice when you take your glasses off that you can't focus on yourself in the mirror? Do you ever notice that? It's kind of hard to. Okay, so if you have weak eyes and you have to have really strong specs, or if you're looking through a good quality telephoto lens, you can't focus. You know, the field of the depth of field is such on a telephoto lens, anyways. It's very narrow depth of field, so you have to be right on the object to have it in focus. All right, and so this means a lens is out of focus if not focused on 10 units behind. So if you were over here and you tried to focus your eyeglasses on the mirror or your telephoto lens on the mirror, it'd be out of focus. You'd have to push it so that it's focused 10 units behind the mirror, and then then Ant-Man would be in focus. All right. And so that's one of the main things to remember about flat mirrors. Now, when we talk about curved mirrors and stuff, which we're going to do in a second, we're going to have to use a lot of the same strategies that we use for flat mirrors. So let's go and talk about concave mirrors first. Okay, can you switch me over to the laptop, please? Okay. And I'll embed this into the YouTube. All right. Let me get my cursor over here. Okay, so the spherical, let me back up. Okay, so here's a spherical mirror. So go ahead and draw a sketch of this. The center of curvature is point C. The radius of the mirror is this slanted line here on the upper side of this bluish triangle. All right, so that's capital R for radius. Now that's a design parameter. Sir Isaac Newton could easily say, all right, I want a radius of 1.267 inches, and then he could grind his mirror to that radius. And it will focus light. Now the light, the one ray of light in this diagram is the red one. And notice that it intersects it comes in parallel to the optic axis. Line CB is the optic axis. All right, it hits at point A. Now line AC, because it's spherical, so we're seeing a cross section of a sphere. Line C is the center. Line CA, line segment CA, is a radius. Therefore, it's orthogonal or perpendicular to the tangent plane, Daniel, of the sphere at that point. All right? So segment AC is perpendicular to the circle, we would say. All right? Now, that's the normal. Okay? And the next thing that we do is we think, all right, let's think of a little tiny pixel of this mirror. All right, now I made it kind of big. That's not really, that's about 40 pixels wide, but all right. So we think of that as a little tiny flat mirror, all right, in dark blue. Now I'm going to replace that with a green line segment, but then we have a flat mirror. We have a normal AC. We have angle of incidence theta, and then angle of incidence or angle of reflection also equal to theta, whatever theta is. And notice that means this has to be theta. All right. And that's the whole secret of this construction here. All right. So here's the little flat. That's a little bit better. A little flat piece of mirror. Now it's actually curved, but we're going to approximate it as a flat mirror. That's why I went through the flat mirror gymnastics with you first. Because what we're going to do is just say that a curved, this is a concave mirror, and we're going to think of this as a whole little, like a little chain of flat, teeny flat mirrors, kind of like this. And you know, if you go and look at these big telescopes, can I ask you, do you know much about adaptive optics? How about you, Kendra? Yeah, there's this thing in astronomy where they have a to diminish the amount of a twinkle. You know, when you look at a star at night, it's a good clear night, which is kind of rare here in Florida, but they do exist, especially if you get out of town. You can see stars. You can see the Milky Way. You can see big stars twinkle, and planets don't twinkle because they're so bright that they don't twinkle. It's the atmosphere that makes it twinkle. And adaptive optics are how astronomers have figured out a way to remove the twinkle for stars as well as planets. And they basically they send a laser beam up into the atmosphere and analyze the reflection off the atmosphere, and then adjust their optics. Just teeny amounts, teeny fractions of a radian. And they have to do that with mirrors that are segments of a big mirror made of small segments of a mirror. And those are the best optics now. So in fact, and it's all driven by a computer, and it really improves the image quality. And now the Hubble Space Telescope is static. It's not adaptive optics. But I think they're putting one up soon called the James Webb Telescope. I think that's adaptive optics. And we got buku adaptive optics down here on the ground. Now, so that's how. So this is basically our theory for curved mirrors, and we're going to use something like this for curved lenses as well when we get to refraction. Now, the other thing that we use is something called the paraxial limit or the paraxial approximation. Now, what does that mean? Paraxial means near the optic axis. So here's the same mirror, and we've got some rays coming in that are way up here. All right. And here's some more a little bit closer to the optic axis. And the paraxial limit says, okay, mentally, forget about all this jazz up here. All right. And just keep the rays, or design your telescope so that you're only getting rays that are coming in fairly close to the optical axis. All right. And so that would be just this one last one here. And that's the one that we had in our diagram a few minutes ago. All right. All right. That's a paraxial ray. And the reason it's a paraxial ray is because if you look, see the lowest down red incoming ray, forget about the ones I erased, those top three, forget about those babies. Now look at the lens here from this impact, this intersection point here, down to its partner on the low side. That's pretty flat. That's not very spherical, or it doesn't look like a sphere. All right, and I'm going to do an even better simulation of it with you for the paraxial limit. So in the paraxial limit, here it is again, the close-up. This is the focal length. The focal length of a spherical lens, if you're in the paraxial limit, is 1/2 R. Now, if you don't have paraxial rays, you're going to get some distortion, some spherical aberration, because they won't all focus at one point. So what this means is, if go ahead and write this down. It's not in the notes, but here's the law. The focal length is F. It's 1/2 R. And so this point F here is the focus, or the focal point of the spherical lens. C is the center of curvature. Focal point's half here. And any ray coming in parallel to the optic axis, if it's paraxial, is going to go through the focus or pretty darn close. So we just say, we'll just call it good. So that's our rule of thumb. In the paraxial limit, every parallel incoming ray reflects off the mirror and bounces out through the focus, just like this one. All right? And that is our, and we're going to do some calculations with that in just a few minutes. But now here's another animation that I made up, and hopefully this, now just look at this. All right. Now, paraxial means near the optical axis. All right, now over there on the right, you can see a part of a spherical surface. Okay, that's a pretty big radii, pretty big radius. Now here's a small one up there. All right, so that's 100 pixels. All right, that circular segment next to the point C is actually part of this same circle. So basically all I did was I drew in the circle, and then I obscured it with a couple squares and rectangles up here to make it look like it's only about 65 degrees worth of this circle over here. So this circle over here is pretty small, 100 pixel radius. This one over here is ginormous. It's 12, I think it's 1250 pixels, almost the entire screen. So the center for this one is off the screen. All right. Now, so there's 100 pixels. All right. So there's my 100 pixel scale, and all right. So there's the optic axis for the small mirror. All right. Now watch this animation. All right. Here comes some rays a few centimeters above. That's a blue one. All right. Now that intersects about 65 degrees of the full sphere if you have a small radius. All right. That blue goes up to almost 1 o'clock here. Actually, that's a little bit before 1, so that's 12:45 or something. No, it's 12:40, 65 degrees. All right. No, wait a minute. That's 1:20. So it's almost 1 o'clock. 60 degrees would be 1 o'clock. All right. So, and then you got 1 o'clock, 1:20 on the bottom as well. So that's not paraxial. All right. It's close to the axis, but your focal length is 100 pixels or 50 pixels actually, and so you have a very bad, you're not going to have a good paraxial image there. Now here's 100 pixels, same size square on the big one. Now here's my center of curvature over here, C2. So that's the center of curvature for the big one. All right. Now if I bring in some rays high and low to this big mirror, I'm going to have something a lot closer to a flat mirror. This doesn't look flat. This looks curved. But now let's look at what happens when we scrub out. Let's get that out. All right, let's scrub out the upper. There's 100 pixels, centered. All right, looks pretty flat. See that little segment? You can see some daylight. All right, see the daylight between the rectangle and the sphere, the spherical surface. Okay, so there it is again. All right, now let me rub out this stuff. All right, and let me rub out this stuff down here. All right, and now that, my wonderful students, that is a spherical mirror, but boy, oh boy, does it look flat. That is the paraxial limit. That is how we make the paraxial limit a reality. We take a mirror and we use a very small portion of the mirror. So that's actually part of a sphere, but it's only a few pixels off of a big sphere. And because it's only a few, it's actually flat. It looks flat. And that means the paraxial approximation is going to be righteous. All right, so there's my focal point right in the middle of the screen. And here's my ray. Bing. And now, look at that ray. It's the same distance above the optic axis as the first one was. But now I'm intersecting just a teeny fraction of the entire, that's like maybe 3 degrees or something. Very small angle. All right, and that's the paraxial limit. And I think even this is a little bit big for true, so if you went up to, some fancy spherical mirror telescope, it'd be even smaller than this. The paraxial limit or the paraxial part of the mirror would be even smaller than this. All right, I think this is even exaggerated. Okay, so there's the radius. It's not 1250, 1200 pixels. And you can see it there. From C2 to the red spherical line, spherical segment is 1200 pixels. So what we do is, in our sketching, we use the straight vertical line segment to represent the paraxial portion of the mirror. And then we use the 3 principal rays. All right, now make notes on this carefully, and make a sketch. The 3 principal rays, and actually there's going to be 4. I'm going to add a 4th that I like to use. All right, here we go. The first principal ray is, it comes in from the object, parallel to the optic axis, and then it bounces out straight through the focal point, F. Right now, the center of the curvature is out here, and half the distance is the focal point. Okay, so point F is the midpoint between the mirror surface and the center. Now this is still, this is, not very paraxial, but it's a lot closer to paraxial. All right, it's good enough for government work today. right, so that's the first principal ray. You figure out, so this red arrow is like the stick figure of the running man on my graph paper a few minutes ago. And right at the top of the arrow, that's the top of his coconut. Now, physics instructors are not usually as good a drawer as me, so they don't use stick figures, they use arrows. So this is kind of a customary thing. You know, they're trying to, not everybody's another Leonardo da Vinci, so we use just arrows most of the time to represent the object. And we're going to calculate with this in a minute. But here's another one. It goes from the top of the runner's coconut through the focus, then way out here, it hits the mirror. And so if that's the case, it bounces out parallel. So this is kind of the opposite of, so here's one, in parallel, out through the focus. This one, in through the focus, out parallel. All right, so they're kind of partners in crime. All right, that's the second principal ray. Now you can use that to locate, you know, where the rays seem to come from, where those rays intersect. That's where your image is going to be. Just like, you know, the image of the running man was behind the mirror. And we're going to do the same thing to figure the image location for concave and convex mirrors. Just a minute here. All right, so that's the second principal ray. Okay, so make sure you have a good sketch of that. And we're going to do some more sketching with this stuff on graph paper. And if you get some graph paper, you can replicate everything for practice. All right, here's the third principal ray. In from the direction of the center. So it starts here at the top of the runner's head. It goes exactly in this direction as if it came from the center. Now, that's like coming perpendicular to the surface. So the angle of incidence is 0. The angle of reflection is going to be 0. It just bounces right straight back. Right? No great shakes about that. It's a bonus. All right? And that one takes you off the paraxial limit a little bit. All right? The number 2 and number 3, you know, you're bringing in a little bit of error there. All right? Number 1 is pretty good. And this one's, so in from the direction of the center, and then out in the reverse direction, because angle of incidence is 0, angle of reflection is 0. It's a straight. So that's like, you know, just coming straight in and coming straight out. You know, if you throw a billiard ball, or if you knock a billiard ball straight into the side of the billiards table, it'll come straight back at you. You know, which you might want, but you know, normally that's not what you want, but that's what would happen if you did that. Now, here's the one that I like, number 4. It goes to the center of the mirror, and then it goes back out at the same angle. And this one's nice because the normal is the line FC, or CF. Right, so here it is coming back out. All right, and that's the one that's one that I like to use. All right. Okay. And the reason I like this one is it's easier to draw. Now we're going to do some dot cam sketching with a lens of focal length 10 blocks, and it's going to be concave. We're going to do it on the document cam. So let's go to the document cam, and we'll do this one. And Kendra and Andrew, I want you guys. Where's Andrew? Oh. Go ahead and start circulating, and just kind of coach these guys as we go. And here we go. And again, I'm going to embed this in the YouTube. All right, here we go. All right, now let's draw an optic axis. And hey, you guys, let me double check my notes. Okay. All right. I'm going to draw right through the middle here I'm going to draw my optic axis first. Let's get this good. Now, if you're using notebook paper, you're going to be in trouble. But graph paper is lovely. All right, now, I'm going to make my lens, or my mirror, I'm going to use a straight line segment to represent the paraxial limit of a spherical lens. All right, so I'm going to put it over here, just choosing a dot. All right, and I'm going to make it 3 blocks tall. And 3 blocks down. All right. Ooh, let me do that over again. I missed my dot. All right. I want it to be right on the. I want it to be right on the line. Okay. Now, you guys, these things you can do with notebook paper. This is if you're using sideways notebook paper. This will. All right. So there's my mirror. Okay. And here's the center of the mirror. Now for this, and we're going to calculate. We're going to calculate the distances and the position. So up here, some specs. Focal length is 10. So 10 blocks. And the distance to my object is going to be 22 units out. Okay, so let me count focal length of 10. So that's, let's see if I can do it. Let me get my specs. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for you guys, that could be 10 units of graph paper. Okay. And then my distance to my object is 22. So 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And that's actually the center, 21, 22. Okay, so here's my running man out here. Now, instead of a running man, I'm going to use an arrow so that it looks more like the book. And I'm going to make my arrow 2 units high. Okay. So that's a sketch. And this is kind of a like I said, a paraxial limit sketch. We're using a straight line segment to represent a spherical mirror. Let me erase a little bit of this. Okay. 3 units high, 3 units down. All right. So that's pretty good. Now, let's draw in some rays. Okay, now the first ray that we're going to draw in is in pencil. The first principal ray. So we're going to bounce a ray from the top of the arrow 2 blocks high to this point 2 blocks high on the spherical mirror. Okay, so that's 2 notebook paper lines there, and then just a straight line segment between them. All right. All right, and so it's coming in this way. Okay, it's coming in this way, and it bounces here. Now it comes out through the focus. So that's this point down here. All right. Now that means it goes 2 blocks down and 10 blocks over. And then it goes another 2 blocks down and 10 blocks over. So it's actually going through this point over here. All right. And so on graph paper, you can do this really nicely. So try to do that. All right. All right. So here it is outgoing. All right. So there's my first principal ray. Now the next one that I'm going to use is the one that goes to the center of the mirror. So I'll call that S, the symmetry point of the mirror. So right here's the symmetry point of the mirror, the center. But I'm already using C over here, so I can't use C over here. But this will be we'll call this S for symmetry point of the mirror. Okay. So my next ray is principal ray number 4. And so that's going to be from the top of the runner. And I'm going to do this one in red. Destiny, can I use your blue marker again? Okay, so I'm going to go, thanks. I'm going to have to get another blue pen or something. Okay, so from the top of the arrow, straight to point S. So that's down 2 blocks and over 22 blocks, because that's the distance to the object. All right. All right, so there's my, oops, I missed my S a little bit there. All right, now, there's my incoming. So I'll give this an arrow here like this. All right. Now, it bounces out at the same angle of incidence. All right. So this angle right here with 2 little curves is the same as the outgoing, the angle of reflection. So that's going to go out along a line down 2 units and out 22. So it's going to go along this line right here. And hopefully that appeals to you. I mean, it's just similar triangles in the paraxial limit. So let me do this one a little bit better. All right. So there's my, all right, there's my, and now look, this is the outgoing ray here. And it looks like they intersect right about here. All right. Now, if you get some graph paper, you can do this over and calculate that exactly. Now, that's where the tip of the image is going to, or the top of the image is going to be upside down. So let me put a dot here, right about there. And this is the object. I'll put letter O over here. And this is the image. And you can see that the image is not quite 2 blocks tall. It's a little bit shorter than that. And it's not 22 units out. It's, I don't know, 18 point something. All right. So it looks like the distance to the image is about 18. Now we're going to calculate that. All right. And here's the formula. Now this is the equation that you use in the paraxial limit. 1 over F equals 1 over DO, object distance, plus 1 over DI, image distance. All right. And we plug in what we know. Is there a question? Okay. So we have 1 over 10 plus 1 over 22, or no, equals 1 over 22 plus 1 over DI. So we can figure out what DI is. Okay. So DI, or let me do this way, 1 over DI. So we got to do some fractions here, but it's not too bodacious. 1 over DI is 1/10 minus 1/22. All right, so that's the same as 22 over 220 minus 10 over 220. Okay, so 1 over DI is equal to 12 over 220 And that means the DI is the flip-flop of that, 220 divided by 12, which is what? 220 over 12 is, what do you get? 18.33. And hey, you guys, that's pretty close to what we actually estimated. So if you're using graph, at least on my graph paper, that's pretty close. All right, so what we would do is we have two significant figures. So we would say DI equals 18, and that's pretty close to what we got over here. So this is, and actually, this is actually a little bit closer to 8. You can see it's a little bit bigger than 18.00, you know, so this is maybe closer to 18.33. So this picture is pretty nice, actually. All right. All right, now questions before we proceed. Yeah.
You need at least two like rays coming from the object.
You need to get two. I like to use these two because they stay in the paraxial zone a lot better than the other, than principal ray 2 and principal ray 3. And that's because the only reason that I do that is because if you're on graph paper, if you're on graph paper, you're out of the you know, if I use an object this tall, it's out of the paraxial limit for a focal length of 10 blocks. That means the radius is 20 blocks, and you know, so even this is a little bit too high to make it. So those other ones, if you have really good paraxial limit and stuff, if you're really close, you know, so like the Hubble Space Telescope is, you know, its focal length is, you know, pretty big. And it's all folded in on itself and stuff like that, and they got it all worked out good. But you know, so they're in the paraxial limit. But even them, they correct that. They correct the image of this Hubble Space Telescope, and everybody else does too. But so paraxial limit, this is pretty good. So, but for classroom demonstrations, I like to use these two because the other ones get into trouble a lot faster. All right, let's swap over to the laptop again. All right. And we're going to keep going here. Oh. Question, Melanie. How did I estimate? Well, when I went to see where my image, look, see where my red and my outgoing red and my outgoing pencil rays intersect there? And I drew a little upside down arrow there. And I said, all right, this is, it looks at it, and then I counted the number of blocks out from the mirror, and it was 18 and change. So I said, okay, so I said it's going to be 18 point something maybe. So I made a visual estimate. You know, I had to eyeball in where to put that little upside down arrow. All right. Now on a computer, Melanie, Matt.
Sorry, I was trying to get out of the way.
On a computer, Melanie, the computer would do all these calculations and then draw it exactly, you know, and draw all the rays nicely. And, you know, a matter of fact, I should make a movie of this because this would be easy to do with, you know, on Keynote. But a computer, if you did all this on a computer, it'd be right on the, you wouldn't have to eyeball anything. But my eyeball upside down arrow there, it's not too bad. It's not too shabby. Does that make sense to you?
Yeah. So you could basically use any of the other principal rays that you.
The other principal rays will bring you out to about the same point. But there's going to be, if you use, but here's the thing. If you use 3, they never intersect at the same point, unless you're extremely lucky or really sloppy. If you're careful, you always get a little bit, you know, the intersection of two of them will be different from the intersection of the other two. You know, so you get a little triangle instead of a point. Where that's if you use three. So if I used any of the other two that I didn't use, if I used one of them, I'd get a little bit of slop. Simply because, like I was saying over here, that the paraxial limit on graph paper like this is stretching it, especially because you'll eventually, it's an approximation, the paraxial approximation. So it's not perfect, but it's pretty close. It does a fairly good job, and on a computer it would look really good. But even on a computer, if we used all four rays, you'd still get a little, a little bit of slop in as to where they intersect, simply because it's an approximation. All right. All right, let's go back to the YouTube. All right, now I'll embed that document cam sketch in YouTube. Now, here's how you deal with a convex lens. It's very similar. The focal point, however, is behind the lens. All right, so this is like if you've ever seen, some little old lady's garden. She has a little thing with a spherical mirror on a little stand, so things look nice and everything, and they reflect light, and it's, it looks nice in the garden and stuff. So that's a spherical mirror, or approximately spherical. So the focal point is inside on the other side, opposite from the silvered surface. So those two rays are bouncing off the silver surface. And notice, though, they come in parallel. They reflect as if they were coming through the focal point, F. So you put that focal point back there, and you use it to sketch in some dotted lines, because there's no ray back there. So you make it a dot. You don't make it red. You make it a dotted line. Okay? And then once you get extend the dotted line outward, then you turn it into a red outgoing arrow, right? And the other rays similar to that. So that's what we're going to do on the next sketch. So let's do another sketch. All right, and this one's going to be with a convex mirror. And it will be, we'll use the same formula, but we have to use a different, oh boy, one last piece of graph paper, good timing. All right, so this is going to be convex. And this one was concave. Where are you guys going? All right. Here we go. All right, now for this one, if you have a convex lens, the focal point is behind the, or convex mirror, I should say. The focal point is behind the mirror. So you would write that, if it's the same size sphere, you would write it as -10. All right. Now we're going to use the same object distance, 22 blocks. All right. And we're going to do a similar construction, except we're going to orient to the focal point behind the mirror. So I'm going to put my mirror a little bit closer to the middle of the page. Let's see, 22. So if I go about here. Okay, so if I put my mirror here, all right, I'm going to make it 4 units high. 4 units down. And so there's my mirror. Here's the symmetry point S. We're going to use that again. Okay, now let me count 22 blocks out to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's the fake focal point. 2, 3, 2, 4, 5, 6, 7, 8, 9, 10. Here's 22. All right, so here's my object. 22 blocks out to the left. Now, let me put my focal point 10 blocks behind the mirror. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so here's my focal point. And I'll put my F up here. And then another 10 units out. Let's see if I can put the center. 3, 4, 5, 7, 8, 9. Okay, the center's off the picture. That's all right. All right, so here's my object. Okay, here's my focal point, and here's my mirror. Now, in parallel, so let's go 2 blocks up on the mirror. All right, and you guys, what we're doing is we're mapping out the tip, the location of the tip. The location of the tail of the arrow is always on the optic axis. So, right, so incoming, like this. Now outgoing, now we go to the focal point and we go to this intersection point. So let me go sideways here. So here's my focal point back here. Now it's going to bounce out like this, as if it's coming from that focal point. It's not going to go from, it's not going to come from that focal point, but it's going to look as if it comes. So what that means is, let's see, this is 2 blocks down and 10 blocks over. So if I go 2 blocks up, 10 blocks over, 3, 4, 5, 6, 7, 8, 9, 10. All right, right here, this will be the right angle. All right. Now, I'm going to draw this stuff as a dotted line. Okay, so here it seems to be coming from the focal point. All right, that's this dashed line. And here's the actual bounce right here. From that point, here's the actual bounce. All right, so there's the outgoing bounce. All right. Now, second ray, I'm going to go from the tip of the arrow to the symmetry point S, and then I'm going to go back out at the same angle. All right, so this one's 22 blocks into S, 2 blocks down. Oh, let me use blue here. This is nice. Thank you, Destiny. I'm going to have to get some additional markers here. Okay, so right from here, from the symmetry point, and this is solid. All right, so this is incoming. And then it bounces back out 2 blocks down from the object. So it goes back through this point right here. All right. And you don't have to, that's true for any mirror. If you go in on the optic axis, bam, you're coming back out this way. So this one is, you don't have to worry about the other focal point. But, so here's my bounce back. So where is your image? Well, the image appears to be in this direction. somewhere back this way. Okay, so here's seems to be somewhere back here. And it also seems the rays from the top of the arrow, they seem to be coming from somewhere back there. So here's how we figure it out. We run the blue bounce out ray backwards as a dashed line behind the mirror. It appears the blue reflection appears to be coming from right back here. All right. So it appears to be coming from back there. And now, my wonderful students, dun, 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 you can figure out the image location right about there. All right. Right now, we're going to calculate this, but let me just kind of trace in right about here. And notice that it's smaller. And it's upright. It's not upside down. You can't put a piece of film here. So we will call that a virtual image. Okay, it's behind the mirror. You can't put film there and capture an image, so it's virtual. It's upright. You know, the other one was upside down, inverted. But you know, this one here, this image here, we got it pretty good, location and height. It's a little bit shorter. It's upside down. It's inverted, but it's real. You could put film here and get an image. All right. And that's for the concave mirror, but not for this one, the convex mirror. So, so that looks to be about 1, 2, 3, 4, 5 point something, almost 6. So let's say DI is about 6. All right. Now let's do the calculation and let the numbers do the talking. All right, here we go. Now we use this same formula, 1 over F equals 1 over DO plus 1 over DI. All right. And so for us, now on this one, we have to put in a negative 10 for the focal point. So 1 over, or for the focal length, 1 over negative 10 equals 1 over 22 plus 1 over DI. And notice that I used the same, I used focal length of 10, negative 10, and I used the same object distance, 22. So I have 220 fractions again. But notice that I've got 1 over DI equals negative 1/10 minus 1 over 22. So that's equal to minus 22 over 220 minus 10 over 220. And that's equal to 1 over DI equals minus 32 over 220. And that's a negative number. So that means that the image is behind the mirror. Okay. So DI is equal to negative 220 over 32. So what is that, about 7? Calculate that. 6.8 something. Okay, so what is it, 6.8 or 6.9? 6.9? Negative 6.875. Okay, right, so negative 6, so two significant figures, negative 6.9. All right, we were fairly close. All right. I was a little bit shady, so I should have put mine out here a little bit further. But you know, your pencils not being infinitesimally thin, you know, you're going to have a little bit of slop, but it's in the right ballpark out here. So that's nice. So there's my image. And we got it pretty good. That's pretty good. Pretty good for government work. All right, now, let's go back to the laptop. Ever see this one from MC Escher? Look at it. Look at it, Alexandra. Look. That's the famous artist MC Escher holding a spherical mirror. He seems to be on the other side of the mirror and smaller. He also seems to be upright, just like what we got, right? In other words, it's not upside down. All right, calculation time. Multiple choice. Go ahead and turn on your clickers again. But you're going to have to do some calculation. All right. Now this is a concave mirror. All right. So do the concave mirror calculation. Oh, hey, guess what? Is that a concave or a convex? It's like a makeup mirror. Makes your face bigger, so it's a convex. Go ahead and circulate. Kendra, could you give me these papers? Those two. Thank you. $30. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, the correct answer is B. 89% of you got that. Good. And I'm not going to go over the solution, but here's the numbers in case you got it wrong. Focal length 1 over 12. And it's positive 12 because it's a concave mirror. Image distance 16. And just work it out. Works out exactly to 48 centimeters. Now we've got a few minutes left. Let's talk about refraction of light. And this gets us to that picture of that guy that looked like he was beheaded in that pool of water. But actually he wasn't because he was smiling. So it's an optical illusion, or as some people would say, an optical delusion. All right, now the law of refraction is called Snell's law. It's based on this diagram. If you look at the upper part, image A, you'll see light coming in from that flashlight at a certain angle, theta 1, and reflected at theta 1. Now, theta 2 is the direction of light that penetrates the water. Now, the index of refraction of water is 1.33, and that's related to the speed of light, as we'll go through. And Snell's law is about the refracted ray and related to the incident ray. So here we go. Snell's law is active or used when you have two different media in which the speed of light differs. Now, the index of refraction, N, is what encodes the speed of light. N is equal to C over V. V being the speed of light in that material medium. So for air, we usually use 1.00. It's not a vacuum, but it's pretty close in terms of index of refraction. But water is definitely slower. So the speed of light in water is a little bit smaller than the speed of light in air. So N is equal to 1.33. And you used, and Snell developed this law. It just basically works off sines and cosines. And it works, in either direction. The bottom image B is, where this would go if you had a flashlight underwater and shone it out of the water. Now that's actually the case. That bottom image is the case of the guy that's beheaded in the first slide from the. And I'll show you how that works probably on Friday. But this calculation. Snell's law, angle of incidence, N1 sine theta 1 equals N2 sine theta 2. You use it for all kinds of devices like lenses, rainbows. The guy underwater that looks like he's beheaded and stuff. And here's the physical reasoning. You can look up any number of this image is from another textbook. It's an old image that I really like, but our textbook doesn't have quite as nice of an image. But now here's what happens. You can see the incident ray, and you can see the wavefronts, lambda 1 between the wavefronts, lambda 2 between the wavefronts in the water. Now it's at this interaction layer here with the water, between the water and air, where things happen. Now what this is like is it's like a marching band that tries to make a right-hand turn. This is making a right-hand turn. The people on the inside of the turn have to slow down. The people out at the end of at the flank of the turn, they got to take big steps, all right, to keep up. Now, if you can't keep up, this is what happens, all right? These rays over here, these wavefronts are going fast, And because they get further, by the time this one has gotten down here, it actually turns the wavefronts by a certain angle. Now, this is where all the trig is worked out over here in this diagram. But it boils down to this idea of a marching band, the marching band maneuver. All right. So so this diagram over here will show you that it's all related to the lambdas, basically. Okay. And the lambdas go a certain distance in a certain amount of time. The frequencies are the same. The lambdas are different. When you refract, you have a different lambda, and the frequency is the same. Now, my wonderful students, we're about to dismiss, but I want to introduce you to the topic for next time, total internal reflection. This is what we use in the design of fiber optics, which the internet would not exist if it didn't have fiber optics. So start reading chapter 25 up to 25.5 on total internal reflection, and I'll see you on Friday. You're dismissed.